Why are humans still striving to develop rockets today? In previous videos, we have explained that rockets are incredibly inefficient transport tools, with a payload efficiency of less than 5%. Over 95% of the rocket's mass comprises its own weight and fuel, and concerns about their launch safety are also significant. While reusable rockets are being developed, their efficiency remains low. There is a clear-cut way to drastically reduce transportation costs and offer much higher safety than rockets, yet aside from science fiction movies, it seems few people discuss this method. You're right, the method is elevators. Actually, the concept of building a space elevator is not entirely unheard of. As early as 1895, a Russian visionary, gazing up at the newly constructed Eiffel Tower, conceived the idea of a space elevator. This visionary was Konstantin Tsiolkovsky, hailed as the father of human astronautics. We mentioned him before in a video about how fast rockets can fly. He lived at the turn of the 20th century and passed away in 1935. It's astonishing that he envisioned such an advanced concept decades before humanity launched its first artificial satellite. Most people might simply pose for a photo in front of the Eiffel Tower, like Newton being struck by an apple, illustrating the disparity in thought between geniuses and the common folk. What did Tsiolkovsky envision standing beneath the Eiffel Tower? He imagined if only we could extend this tower into space, wouldn't it be possible to travel to space via an elevator? Indeed, this was the earliest conception of a space elevator. Yet, over 130 years since this idea was first proposed, and more than 90 years after Tsiolkovsky's passing, with rapid technological advancements spanning two industrial revolutions, the second electric revolution, and the third information revolution, we still seem far from realizing a space elevator, and it's even rarely discussed. Why hasn't something so obvious to a 3-year-old been achieved yet? To understand this, we must delve into the materials at humanity's disposal. Imagine you're given a 10-centimeter steel bar and asked to bend it. Is it difficult? Now, try bending the same bar if it's 10 meters long. You'd know instinctively that it's much easier to bend. This is due to material instability. The critical point for instability failure in objects of the same diameter is inversely proportional to the square of their length. Longer objects bend more easily. Suppose a 100-kilometer high space elevator used the same material as the Eiffel Tower, it would be over 300 times taller, and if it had the same thickness, its load-bearing capacity would be 100,000th that of the Eiffel Tower. In that case, it wouldn't even need to reach 100 kilometers. It would collapse under its own weight at just 10 kilometers. Is there really no way out? Let's change our perspective. Can you help me pull the steel bar apart, no matter how long it is, 10 centimeters, 10 meters, or even 100 meters? You probably wouldn't even try, right? Because you know that it's impossible. What does this tell us? It shows that under natural conditions, a material's tensile strength is far greater than its compressive strength. So, instead of building upwards from the ground, why don't we build downwards from the sky? Haha, you've got it. In 1957, Yuri Artsudanov, a Soviet engineer, also came up with this idea. The height of this structure cannot be too low because the rope needs to remain relatively stationary with respect to the ground. Therefore, the optimal height is 35,786 kilometers, which is the geostationary orbit of artificial satellites. A satellite in this orbit takes exactly 24 hours to circle the Earth, matching the Earth's rotation. An artificial satellite in geostationary orbit acts like a nail, anchoring this more than 35,000-kilometer-long rope in space and allowing it to hang vertically to the ground. This is the basic concept of the second-generation space elevator. Instead of building a towering structure from the ground, it becomes a rope, and the force it bears changes from compression to tension, significantly reducing the material requirements. the space elevator scheme finally becomes much more feasible. But can we start building it right away? This monumental project would dwarf any historical endeavor in terms of its significance. So why is it still confined to the realm of science fiction, with little discussion even in the news? It's similar to comparing tree, 3, and Graham's number, as I mentioned in a previous video. While tree, 3, vastly exceeds Graham's number, even Graham's number is a godlike figure for humanity. Even the first level of Graham's number is incredibly large. What you perceive as a hanging rope is actually a towering mountain suspended upside down. Let's do a simple math problem. A steel bar with a diameter of 1 centimeter and a length of 1 meter weighs approximately 0.617 kilograms. A steel bar spanning over 35,000 kilometers would weigh over 22,000 tons, and that's under ideal conditions. In reality, the tension increases towards the top and decreases towards the bottom. Therefore, the rope needs to be thicker near the top and thinner towards the bottom, resembling a slender cone. The ratio of the cross-sectional area at the base to that at the tip is called the taper ratio. By precisely calculating this taper ratio, we can ensure that each part of the rope bears equal tensile force, maximizing its strength. Does such a calculation method exist? Scientists have long considered this issue. By considering the gravity acting on each point and subtracting the centrifugal force due to Earth's rotation, we can determine the force on the rope. Dividing this force by the cross-sectional area at that point gives us the stress it bears. We simply need to equalize the stress at each point. Through this analysis, we arrive at a formula. After substituting relevant parameters, the formula simplifies, making it seem quite straightforward. The specific strength is the ratio between a material's tensile strength and its density. Let's take a look at the specific strengths of some materials. For stainless steel, its specific strength is approximately 63,100 newtons per square meter per kilogram. Plugging that into the formula. Oh, my God! The result is 2.2 times 10 to the power of 334. This means if the bottom diameter were 1 centimeter, the top diameter would be 2.325 times 10 to the power of 317 light years. Whereas the observable universe's diameter is about 93 billion light years. The top diameter would be 2.5 times 10 to the power of 307 times the size of the observable universe. Oh my God! Oh my God! Oh my God! I have to say it 3 times to express my amazement. To me, this number is no less astonishing than Graham's number, or tree, 3. Using steel as the material for a space elevator. Let's just say that's not feasible, and we should look for other options. Let's explore the specific strengths of various materials and find the best one. Here's a direct look at the most powerful material that humans can currently produce, carbon nanotubes. Discovered by Japanese scientist Sumio Iijima in 1993, these materials resemble graphene but in a tubular structure. Carbon atoms are arranged in a honeycomb pattern, forming a tube. Thanks to the unique structure of carbon atoms, this remarkable material is inherently bound together by powerful electromagnetic interactions between atomic nuclei and electrons, giving it exceptional strength. If you need a comparison, think of diamond, the hardest substance in nature. Based on this, carbon nanotubes exhibit astonishing tensile properties. What about their specific strength? According to Wikipedia, carbon nanotubes can withstand up to 46,268,000 Newton meters per kilogram. Plugging that into the formula, we get a specific strength of approximately 2.85, bringing us back down to Earth from the realm of the gods and aligning perfectly with our needs. This undoubtedly provides a solid foundation for the concept of a space elevator. Of course, while the ideal is promising, reality can be harsher. It may be challenging to achieve such extreme performance in actual production, but this data is still encouraging and within an acceptable and hopeful range. With the material aspect positively addressed, the urge to put it into practice arises. However, patience is key. Carbon nanotubes are excellent, but their production process used to be a significant obstacle. Early on, methods like arc discharge, involving sparks from graphite electrodes, yielded only minute quantities, with questionable purity. Then, chemical vapor deposition emerged as a preferred method. In simple terms, hydrocarbon gases are decomposed under high temperatures and in the presence of a catalyst, with carbon atoms linking up to form nanotubes. Since impurities escape as gases, the resulting nanotubes are highly pure. However, the challenge lies in the chaotic growth patterns and strong dependence on catalysts, limiting large-scale production. Fortunately, the scientific community has not stopped its progress. In 2018, the team led by Wei Fei from Tsinghua University successfully achieved a macroscopic and ordered arrangement of carbon nanotubes by innovatively enhancing the activity of catalysts and combining with the airflow focusing technology. Its tensile strength has reached a staggering 80 GPa, equivalent to withstanding a pressure of about 800,000 atmospheres. From the perspective of strength alone, it has infinitely approached the dream destination of building a space elevator. However, regarding the length of the individual carbon nanotubes they have manufactured, the claim of being as long as 50 centimeters is, of course, just a joke. It is noteworthy that Tsinghua University in Beijing holds a globally renowned and top-tier position in carbon nanotube technology. Although Professor Wei Fei ambitiously announced that they are striving to achieve breakthroughs at the meter scale and beyond, the current technological bottleneck lies in maximizing the utilization of catalyst activity, with experimental data indicating that this activity has already been nearly exhausted. Therefore, without a fundamental leap in preparation technology, achieving nanotube lengths of tens of thousands of kilometers remains an unattainable dream. Does this mean that the cable issue for the space elevator has hit a dead end? The answer is no. The charm of science lies in exploring possibilities amidst impossibility. Given the unavailability of ultra-long nanotubes, a group of American scientists, fueled by their vision for the space elevator, embarked on exploring alternative solutions in the early 21st century. Their strategy was, if one fails, try many. If a single material is insufficient, innovate through mixing. They created carbon nanotube composites by ingeniously combining carbon nanotubes with other materials to enhance the overall performance. To improve friction and adhesion, they envisioned adding micronail-like structures to the nanotubes. Experiments have shown that when the proportion of carbon nanotubes in the composite exceeds 50%, the tensile strength can reach 5G. Further speculation suggests that at a specific content level, the tensile strength could soar to 150 G. Furthermore, they proposed an innovative idea of altering the cable's shape from traditional round to square. This design not only enhances the cable's flexibility, facilitating the ascent and descent of equipment, but also bolsters its resistance to meteorite impacts. A square cable may suffer localized damage upon impact, whereas a round cable might rupture entirely. Based on these innovative concepts, in 2006, scientists at the Los Alamos National Laboratory in the U.S. designed a cable plan with a width of 1 meter and a total weight of 650 tons. If this elevator became a reality, its single-trip carrying capacity could reach 150 tons, virtually matching the payload of a single launch of Elon Musk's Starship and even surpassing the total payload of all rocket launches worldwide, excluding China and the US, in 2021, which is truly remarkable. Regrettably, all of this remains at the laboratory stage, reminding us that while dreams are beautiful, they require solid groundwork in reality. The grand blueprint for the space elevator may require more time and technological accumulation to become a reality. I am confident that each of you who clicked in did not merely seek an answer about the short-term unfeasibility of the space elevator. Therefore, let us embark on an imaginative journey and explore, once the cable challenge is overcome, how should we proceed with building this dream space elevator? The primary task is how to deliver this astonishingly heavy cable into the upper atmosphere. Given its colossal size and weight, we could consider a phased launch strategy or directly establish a production base in space, utilizing carbon resources from asteroids to manufacture carbon nanotubes on-site and gradually release them towards the ground. However, here we must address a crucial issue. Geosynchronous satellites maintain stability at an altitude of over 30,000 kilometers due to a delicate balance between their tangential velocity and gravity. As the cable extends downwards, this balance will be disrupted, and the cable's increasing weight will threaten the satellite's stability. To tackle this challenge, we introduce the concept of counterweights. By releasing cables or placing heavy objects, such as space stations, at the other end of the cable, i.e. extending towards space, the centrifugal force generated by these counterweights can counteract Earth's gravity, thereby maintaining the stability of the satellite and cable system. In this way, the satellite becomes the balance point in this system, with forces on both sides canceling each other out. Next, we must consider the landing site for the cable. Since geosynchronous satellites can only reside above the equator, the optimal choice undoubtedly lies in finding suitable land or sea areas on the equator to construct our ground base. Considering the scarcity of land resources on the equator and the fact that this is a monumental project concerning the fate of all humanity, along with geopolitical and other factors, choosing to establish a floating island on the high seas, similar to an oil drilling platform, would be a flexible and feasible solution. Regarding the elevator's lifting mechanism, due to the unique structure of the cable, thicker at the top and thinner at the bottom, direct suspension through the cable is obviously impractical, necessitating the elevator's ability to climb autonomously. Now, let's delve into the core issue of power supply. The operation of elevators is inherently reliant on energy, and we have three potential solutions. First, self-sufficiency, such as installing solar panels or carrying a small nuclear reactor, though the latter may impose a significant burden. Second, wireless transmission technologies like laser-powered energy, albeit heavily influenced by weather conditions. Third, harnessing the conductivity of carbon nanotubes to supply power directly through the cable. However, the transmission efficiency and stability of long-distance carbon nanotube cables, along with current manufacturing capabilities, pose significant challenges to this approach. In summary, the construction of a space elevator necessitates not only technological breakthroughs in cable technology, but also addresses the issue of power supply, which might be the second most formidable challenge after the cable itself. Looking ahead, we may adopt a comprehensive power supply strategy tailored to the complex demands of the space elevator. Beyond Earth's atmosphere, we can fully leverage solar energy or laser technology for energy acquisition. Within the atmosphere, more traditional yet reliable methods like cable transmission or wind power generation might be relied upon. Given the scale and complexity of this project, every step requires meticulous planning and calculation, as the optimal solution often deviates from the most intuitive or simplest one. When it comes to the completion of the space elevator, the benefits it will bring will be far-reaching and extensive. First and foremost, it will greatly reduce the cost of going into space. Although the initial investment is huge, its long-term social and economic benefits are immeasurable. It is estimated that with the large-scale operation of the space elevator, the cost of entering space per kilogram is expected to drop to about $200, which means that ordinary people only need to spend about $10,000 to realize the dream of traveling to space. This change will undoubtedly lead mankind into a truly big space age. Space stations, spaceports, and even interstellar cities and other ideas will gradually become a reality around the space elevator. Furthermore, the space elevator will revolutionize the way we launch satellites and spacecraft. For geosynchronous satellites, they will no longer require complex rocket launch procedures, but can be easily released at the appropriate position on the space elevator. As for spacecraft that need to escape Earth's gravity, they can continuously ascend within the space elevator until reaching an altitude of approximately 50,000 kilometers, where their speed will be sufficient to achieve escape velocity, enabling them to effortlessly fly to the moon or other deep space destinations. This transformation not only simplifies the launch process, but also significantly enhances launch safety and efficiency. Our spacecraft, to achieve the second cosmic velocity and escape the solar system, will no longer require intricate calculations, gravitational slingshots, or lengthy waits for opportune moments. They simply need to ascend to the corresponding height via the space elevator. Moreover, the space elevator serves as the foundation for interstellar mining. Once interstellar mining matures and countless incremental resources are available, it will fundamentally alter the situation where humanity competes fiercely, or even resorts to war, for various resources. Only then can humanity achieve long-term peaceful development. Thus, the space elevator is not only a milestone in aerospace technology, but also a catalyst for human societal progress and harmonious coexistence. It heralds the arrival of a new era where resources are no longer a source of conflict, but a precious treasure to be jointly explored and utilized by humanity. With the flourishing of interstellar mining, human society will enter an unprecedented era of prosperity and peace, where nations will increasingly collaborate and communicate to share the blessings bestowed by the universe and jointly face the challenges and opportunities presented by cosmic exploration. The completion of the space elevator and the rise of the interstellar mining industry will profoundly alter human thinking patterns and worldviews, making us realize that Earth is merely a tiny planet in the vast universe, and that humanity's future lies amidst the stars and galaxies. Guided by this shared vision, humanity will forge ahead hand in hand, striving towards an even more splendid cosmic civilization and achieving true long-term peace and sustainable development.